Welcome to this explainer. Today, we are tackling a genuinely fascinating mystery right at the absolute bleeding edge of artificial intelligence. We constantly hear about autonomous discovery systems, frameworks like OpenEvolve or TT Discover being hyped up as these ultimate tools for automated AI research. There's this prevailing narrative out there that these systems act like universal master keys for discovery. The idea is basically that you can just plug any problem into them and boom, they'll autonomously output these brilliant solutions. But are they truly the universal master keys we've been led to believe they are? Well, a massive new piece of computer science research set out to answer exactly that question. And honestly, their findings are going to completely upend how we think about automating AI discovery.
Okay, let's dive into this. We've got a quick 4-part roadmap today. First, the universal harness myth. Second, unpacking the mega experiment. Third, the generalization problem. And finally, the adaptive allocation solution.
All right, Section 1, the universal harness myth. Is it actually a silver bullet?
In the super fast-paced world of AI development, it is so tempting to just look for a silver bullet. The AI community often treats these autonomous discovery systems like general-purpose tools. Build it once and it supposedly works everywhere. But to really understand why this is a myth, we have to establish what we're actually working with here. So what exactly is a discovery harness? Well, a discovery harness isn't just some single algorithm or a basic script. It's a highly complex composite system. Think of it kind of like a master recipe for automated AI research. It takes several really distinct, intricate design choices and throws them all together to automate the process of making discoveries.
Just look at how these specific ingredients have to come together to form that recipe. A harness has to manage archives of previous discoveries. It has to handle parent selection to decide exactly which ideas to build on next. It requires exploration strategies to navigate these massive spaces of possibilities. And crucially, it needs budget allocation to figure out how much computational power to actually spend. So when researchers use a discovery harness, they're not just picking a tool. They are committing to a highly specific, rigid combination of all these elements.
Moving on to Section 2, unpacking the mega experiment. Let's test these recipes. If these harnesses are complex recipes, how do we actually know which one is best? And this brings us to a massive friction point in the field. The harsh reality of AI discovery is that these runs are incredibly expensive, and they are inherently stochastic, meaning there's a huge degree of randomness in how they turn out. Because of this, researchers often test out their new harnesses using very few independent trials, and that leads to run-to-run variants masking real methodology improvements. You might run a brand new harness twice, get a fantastic result, and tell everyone you've built a master key. But in reality, you probably just got lucky with the random seed.
To actually cut through all this noise, the researchers behind this paper decided to do something totally unprecedented. They systematically decomposed OpenEvolve-style evolutionary search, along with the TTT Discover search harness, right down into their base constituent components. And from there, they created and evaluated 30 distinct budget-matched harnesses.
But they didn't just test these 30 harnesses on one simple task. To really put this idea of a universal master key to the test, they ran these evaluations rigorously across 12 completely different model problem pairs. This ensures that whatever results they get aren't just some fluke based on one specific type of AI model or a single coding problem. Now, to test those 30 harnesses across those 12 model problem pairs, and to do the repeated trial statistical analysis required to prove it, the researchers utilized a staggering 3.1 million LLM rollouts. They didn't just take a guess here. They brought an absolute mountain of statistical receipts to back up their point. Section 3. The generalization problem. Here comes the massive plot twist. So, what actually happens when you throw 3.1 million rollouts at the assumption that we have universally superior harnesses? Well, the data delivered a huge plot twist. They came to one inescapable conclusion, and I'll quote it directly. No fixed harness is reliably superior across the evaluated model problem pairs. Let that sink in for a second. Out of 30 different recipes, tested across 12 different environments, literally not a single one could claim the crown of being a universal master key. The myth is officially busted. And the plot twist goes even deeper when you start comparing the complex, heavily engineered fixed harnesses, like the variants of OpenEvolve, against much simpler alternatives. You'd naturally assume that the highly complex systems built for modern AI research would consistently win out, right? But surprisingly, the researchers found that these complex variants generally underperform compared to much simpler alternatives when you evaluate them at this scale. The complexity was actually getting in the way of reliable generalization. So, what this means is that developers need to completely change how they view these systems. Harness choice is a hyperparameter, folks, not a universal recipe. Just like you would meticulously tune a learning rate or a batch size for a specific neural network, you have to tailor your discovery harness to the specific problem and the underlying model you're working with. You absolutely cannot just copy-paste a harness and expect optimal results.
Finally, Section 4, the adaptive allocation solution. Let's look at the optimal solution.
The researchers didn't just point out this massive flaw and walk away. They actually used their massive dataset to find a way forward. If we can't pick one perfect harness in advance, how on earth do we efficiently manage our compute? Well, by analyzing all those millions of rollouts, they discovered a really foundational property. Early discovery progress predicts final performance. In simple terms, if a particular harness starts off strong, it's highly likely to end up performing well by the end of the run. And this predictive property is the exact springboard needed for a beautifully mathematically sound solution.
They built this into an elegant survival of the fittest mechanism called the budget-matched adaptive allocation experiment. Instead of just guessing which harness to use, you follow 3 steps. Step 1, start multiple different harnesses simultaneously. Step 2, monitor them and quickly prune the weak partial runs that just aren't showing early progress. Step 3, reallocate your computing budget exclusively to the stronger survivors.
When they tested this adaptive approach against the traditional methods, the results were totally definitive. The adaptive allocation method easily outperforms committing to a random fixed harness. And even more impressively, it outperforms a non-adaptive ensemble, which is where you just run a bunch of different harnesses from start to finish without pruning or reallocating anything. Online adaptation simply dominates. The takeaways from this explainer fundamentally shift the paradigm of automated AI discovery. We need to move away from fixed harness selection and completely embrace online adaptation guided by early performance. Furthermore, the researchers have given the scientific community a massive gift here. They've released all their run pools, including baseline null distributions for every single model problem pair they tested. This provides a reusable, data-rich statistical infrastructure, meaning any future harness proposals can be rigorously tested against a true baseline. That variance illusion we talked about, it doesn't have to happen again. I want to leave you with this final provocative thought to ponder regarding your own projects. How much compute are you currently wasting on a fixed harness? Because if you're relying on a single, universally assumed recipe for your automated discoveries, this research proves you are likely burning time, money, and computing power on an absolute illusion. It's time to adapt. Thank you so much for joining me for this explainer, and keep exploring.